right, students, so we got here number 6, which is a great problem because it's connecting Euler's method and then solving differential equations analytically and then comparing them. So this is a really good problem to work through yourself before you watch me do it on this video. So here's what we're going to do. Start out with y of 0 equals 1, and then we're going to use our h value of 0.5. So if we plug in our initial values into our differential equation, we get 1 minus 0 times 1 over 4 minus 0 squared, which is 1. So my initial slope is 1, and that means that my next y value is obtained by doing my slope of 1 times my h value of 0.25 plus my initial value of 1. And so I guess that means that I have 1.25. So this was the first estimate, so I'll call it y1. And so now I have an x comma y, and I'm saying that when x was 0.25, the y value is approximately 1.25. Sorry, this should be approximately. Okay, substitute that in. dy dx equals 1 minus 0.25 times 1.25 over 4 minus 0.25 squared. Some of you might be able to automate this process on the calculator. It is a bit of a pain in the butt to just go through, but you can do it. Just type it in. Okay, so typed in everything to the differential equation. Got approximately 0.92. So my next approximation for the y value is 0.92 times my step, my h, 0.25, plus my previous y value, 1.25. And that's going to be approximately 1.48. All right, let's slide that down to our next approximation. So we are approximating that the y value at 0.5 is approximately 1.48. Let's do our dy dx again. 1 minus 0.5 times 1.48 over 4 minus 0.5 squared. Okay, I'm just going to go through. Let's see. There we go. So I got everything into the calculator. Enter. That's approximately 0.8. Great. So my third y value is 0.8 times 0.25 plus 1.48. And that gives me a third approximation of 1.68. And so that's the approximation when x is 0.75. Okay, we're almost there. One more time. Dy over dx is, what do we got? Okay, 1 minus x times y over 4 minus x squared. Changing the values. And I get 0.6, 0.63. And so my fourth one, and this will be my last one, my fourth is going to be, 0.63 times 0.25 plus 1.68. And I get an approximation 1.85. 1.84. 1.84. Okay, so let's just keep that value. That's basically Euler's method. You just keep using the slope, and you slide h steps to the right to get your next y value. So now we're going to try to solve it using an appropriate analytical method. Great. So let's clear the screen. When I rewrite the differential equation dy dx plus x over 4 minus x squared y equals 1, you should recognize this is an exact equation. So you're going to multiply by the integrating factor e to the x over 4 minus x squared dx, which is a u substitution. 4 minus x squared du is negative 2x dx. And so our integrating factor becomes e to the negative 1/2 integral of 1 over u du. Okay, so that becomes e to the negative 1/2 natural log of u, which can then be, looks like the e in that, so that would be a cancel out the natural log, and so you just have u to the negative 1/2, but we want to get back to x, so 4 minus x squared to the negative 1/2. So let's take our original differential equation and multiply everything by I. So we have 4 minus x squared to the negative 1/2 dy dx plus, this is going to get a little hard to fit on here, but we have our integrating factor, 4 minus x squared to the negative 1/2 times x over 4 minus x squared y is equal to 1 times our integrating factor. So I'm just going to cheat and write capital I there. The point is, the left side of the equation is the product rule of 4 minus x squared to the negative 1/2 times y. You can work it out for yourself, and that's going to equal the integrating factor. So the left side just becomes 4 minus x squared to the negative 1/2 times y, and the right side is the integral of that. Oh dear. Okay, so that's a little bit nasty. So we got to do the integral of 1 over square root 4 minus x squared dx. I believe, let me pause and look at the formula sheet for a second, because I believe we can, this is a arc sine or an arc cosine. Let me look it up. All right, so I was right that when it's a squared minus x squared, you can have it be arc sine. So we have the left side is just getting copied down again. The right side just becomes arc sine of x over 2 plus c. And then we also know that y of 0 is equal to 1. So we can substitute that in here to solve for c. So we have 4 minus 0 to the negative 1/2 times 1 equals the arc sine of 0 over 2 plus c. Because sine of 0 equals 0, arc sine of 0 equals 0. So that goes away. 4 to the negative 1/2 is the square root of 4 on the bottom, so 1/2. And so 1/2 is our c value. We are almost there. We just need to divide and rewrite everything in terms of y. So I'm going to get rid of some of this business here. Clear up space to write our answer that we found analytically. Okay, we're almost there. So here is our solved y. Y equals arcsine x over 2 plus c, which turned out to be a half, divided by 4 minus x squared to the negative 1/2. I don't really like the negative 1/2 on the bottom, so let's just bring it up top. 4 minus x squared to the half times arcsine x over 2 plus 1/2, like so. And now, finally, the value of y when x is equal to 1. We have 4 minus 1 to the 1/2 arc sine of 1/2 plus 1/2. Great. I am just going to type this into the calculator. That's silly to try to do that by hand. So 4 minus 1 to the 1/2 parentheses inverse sine of 1/2 plus 1/2. There we go. All of that work, all that hard work, and we got 1.77. And if you look, I have the previous Euler's method gave us 1.84. Pretty darn close. All right. So if we sketched it, we would see that the analytical method gives us a slightly higher value. That lower value. Euler's method was a overestimate there. And you can look at the concavity of the curve to try to understand why using tangent lines would be an overestimate or an underestimate. So thanks for watching. Let me know if there's anything I should go into more detail about.